we're getting into chapter 6 today. And so chapter 6, we're going to kind of introduce today. We're going to kind of bring out the preliminary concept, which is why do things bond? What kinds of bonding exist and why does it happen the way that they do? We'll dip a little bit into ionic bonding today. And then most of tomorrow is going to be about ionic bonding and ionic bond like nomenclature, how to name these compounds. And then Thursday we'll focus on the molecular side and looking at covalent compounds and how they're put together and just some things that we can kind of attribute and say about those compounds, in addition to learning how to name them as well. So there's going to be a lot going on here. Luckily for us, it's kind of thematic. So we can kind of put things into 2 big categories, and if we can understand each category individually, there is a little bit of overlap between them, which we'll actually talk about mostly today. So the first half, maybe even a little bit more of this chapter, is all about ions. And so we need to get into, well, what is an ion? Now, our book gives us a little bit of direction here. Ions form positively charged ions when they lose electrons, negatively charged ions when they gained electrons. But we're kind of missing the fundamental it. What is an ion? An ion, in its very simplest kind of definition, is an atom that carries a charge. Now, if you go back to what we were talking about in chapter 4, we talked about this idea of neutrality. Every proton has a matching electron and vice versa. Well, that works well if we have atoms. But if we have something that is not charge balanced, is not neutral, then we deal with what are called ions. And ions are all about charge. And that charge is all about the number of electrons. So if we have a neutral atom, then we have even numbers of protons and electrons. So even numbers of protons and electrons. See if I can do this another way here. Let's think about this graphically for a second. If this purple mark represents the number of protons, and this blue mark represents the number of electrons, then we can see that there would be 3 different possibilities here. There would be the possibility where we have equal numbers of both. There'd be the possibility where we would have more protons, and there'd be the possibility where we'd have more electrons. And we would have 3 different names for those. The one in the middle, we know already. This one's neutral. When we have fewer electrons, we have more protons. Again, this is just what we need to think about. What are the charges on these things? Protons have a positive charge. Electrons have a negative charge. So if I have more protons, I have more positive. This would be a positive ion. Over here, I've got more electrons. This would be a negative ion. Now, the thing that we want to notice is that in each of these cases, barring for some minor differences, the purple bar is exactly the same in all three cases. And we got to remember, that's always going to be the case. If I'm looking at a sample of sodium, that sodium is going to have 11 protons, regardless of how many electrons are there. But if there are 11 protons and 11 electrons, then we're talking about a neutral atom of sodium. If there are 11 protons but 10 electrons, now we're talking about a positively charged ion. There are 11 protons but 13 electrons, now we're talking about a negatively charged ion instead. So the important thing to remember is that we really haven't changed anything from the nuclear standpoint. This week, it's all about electrons. So if we kind of go back the past 3 weeks, chapter 4 talked about the idea of the atom in general, the fact that there are protons, neutrons, and electrons inside of that atom. Last week, we talked about nuclear chemistry. We talked just about that nucleus. We kind of ignored the fact that electrons even existed when we were talking about alpha decay versus beta versus anything else. This week, we're going to largely ignore the nucleus, because when it comes to atomic bonding kinds of principles, the nucleus really has nothing to do with it. It's all about the electrons. And so this idea of ions come from the idea that it's the electrons that are going to drive the bus here. And how many electrons I have versus how many protons I have are going to give me a real clear picture of what the charge of that ion or atom is going to be. So the kind of fundamental principle at play here in this overall concept of bonding is something called the octet rule. The octet rule governs most of the bonding that is going to take place that we are going to discuss in this course. And the idea is relatively simple. The goal of every single atom is to get to 8 valence electrons. Now, back in chapter 4, when we made this original kind of drawing of the periodic table, we talked about, valence electrons. We kind of threw it away. Okay, there are this many valence electrons in this atom, and there are this many in this atom. Now it becomes important. And what we need to remember is that those group numbers, those numbers that we put in A form on top of the table here, those numbers tell us the number of valence electrons for that given element, or for that given group, which contains, a number of elements. And the goal of bonding is to get to 8, which, when we think about it from that perspective, that's exactly why those noble gases in group 8A, group 18, that's why they don't react. They already have 8 valence electrons. And since they already have 8 valence electrons, they have no business trying to bond to get to 8 valence electrons. They're already there. But now we can split, based on this idea of the octet rule, we can split bonding into two different forms. The first form of bonding, ionic bonding, is where atoms get to that 8 valence electrons by transferring electrons between each other. What that generally looks like metal atoms will lose electrons and non-metal atoms will take electrons. In the course of a chemical reaction, these two processes of giving and taking happen simultaneously and almost instantaneously between the two. Since those metal atoms are losing electrons, they will tend to have a positive charge. And since those nonmetals are taking those extra electrons, they'll tend to have a negative charge. And so if we're looking ahead to tomorrow, that's going to be the kind of the fundamental thought of tomorrow is how many electrons get gained, how many get lost, what are the ionic charges that we would expect on a given element based upon where it is on the periodic table. So that's ionic bonding. Now, in addition to the formation of those ions, what really holds ionic bonds together is attraction. You've heard the expression that opposites attract. Well, this is one of the places where that's coming from. If I have a positive ion and a negative ion, they are going to be naturally attracted to each other based upon their opposite electrostatic capability. And that's going to hold them together. And that's why if we look at ionic compounds, they tend to be kind of hard to break apart, at least from a chemical standpoint. From a physical standpoint, yes, I can take rock salt and a hammer and turn it into powder salt relatively easily. But from a chemical standpoint, I can hammer that salt all I want. The ions that make up that salt are going to be well attracted to each other. They're going to stay attracted to each other. Covalent, on the other hand, that's going to be the theme for Thursday. This is primarily a non-metallic move. Nonmetals behave covalently, and what happens there is because they have large numbers of electrons already kind of around them, instead of giving up electrons, which would be very difficult for them, they tend to share electrons with each other. But the end goal is exactly the same. I got to get to 8. 8's the magic number. So this illustration kind of just shows what's going on here. The M refers to a metal atom, NM refers to a non-metal. And so what we can see in the top one here on the left is the metal is giving its electron to the non-metal. The result is I've got a metallic positive ion and a non-metallic negative ion. And those two ions are attracted to each other based upon their opposite charges. In covalent bonding, what we see most often is the sharing of unpaired electrons. So we'll get into on Thursday especially how to draw these diagrams of what they kind of mean. Once we do that, it'll actually be really easy to kind of predict what that structure looks like, how that nonmetal is going to bond. Because what we'll be able to do is we'll be able to look at the dot diagram and say, oh, that atom has 3 unpaired dots. It's going to make 3 covalent bonds. I just look at the number of unpaired dots in the diagram, and it'll tell me exactly how many bonds it's going to make. Important distinction going to or could. For most of our purposes, we're going to go with going to. There are a couple of weird exceptions in there, but for the most part, we're pretty confident that the majority of the compounds we're going to look at are going to hit the octet rule. Okay. So let's abandon this for just a minute, talking about the metals. Let's go to our periodic table here. And so on that periodic table, we've got listed the 3 metallic groups. 1A, the alkali metals, 2A, the alkaline earth metals, 3A, for lack of a better term, we're going to call this the boron group. Now, if we recall, and again, we went through this very quickly, kind of in passing one day, but we understand that these group numbers also give us the number of valence electrons for that substance. And so when we look at these, we have to come to the kind of conclusion of, well, what makes the most sense for this atom to do? So if I look at group 1, to get to 8 valence electrons, it can either do one of 2 things. It can gain 7 electrons, 1 plus 7 is 8, or it can lose the electron it has, and while that would empty out the energy level that that 1 electron was in, if we go backwards, we think about the periodic table as kind of like a wrapping cylinder as opposed to a planar table. Well, going backward from 1A by 1 spot puts us in group 8A, the noble gases, which have the appropriate number of octet. So you've got the option of losing 1 electron or gaining 7. Which one sounds easier to do? Just to lose the 1. Well, if I lose the 1, I now have 1 fewer electron than I did before, which means I've got 1 extra proton. My charge here is going to be +1. So every atom in this group will form +1 ions when they make ions. And they're not going to form any other kinds of ions. Because if they do, then they go outside of the octet rule. So it's not going to make a whole lot of sense for sodium to make a +2 ion, because if it loses 2 electrons, it now looks like a halogen instead of a noble gas. Well, what was the point of that? Joel?
So there will never be an element with 9 valence electrons?
Nope. Nope. No 9 electron valences, because what happens is once that 8th one is added, that 9th one goes into a new energy level. There's no space for the 9th electron. So what happens is that the atom has to expand to accommodate that new electron.
Even if we were to discover new elements?
Hold the same structure. This goes all the way to Argon-S in element 118. If I add one more, if I somehow developed a way to develop element 119, that electron would be by itself in a new energy level. It would not pack itself into the same energy level as these 8 electrons of augnescent. All right, let's look at 2A, the alkaline earth metals. Same series of logical kinds of progressions here. I have either lose 2 electrons. If I lose 2, I wrap around the back, I end up at the noble gases, or I can add 6. So lose 2 or add 6. Again, losing 2 seems to make the most sense. So from that perspective, we would expect a charge of +2 on those alkaline earth metals. And again, +2 is going to be the only charge that they carry. They're not going to carry any other charges because, again, it doesn't make sense for them to do so. If an alkaline earth metal only loses 1 electron, well, that doesn't do it any good. Now it just has 1 electron instead of 2. It's no closer to the octet than it was before. So the point of the octet rule is it's going to give us a very clear-cut definition of what an atom needs to do to become bonding stable. All right, last one here, group 3A, the boron group. Now, boron is a metalloid, so it kind of fits in both. What we'll see with boron is that it does have a tendency to form covalent bonds rather than ionic bonds, but it doesn't actually obey the octet rule when it does. More on that Thursday. When it does participate in ionic bonding, it's going to have the same logic as all of these others. And the logic is, again, 3 lose or 5 gain. Again, the math seems to work out. Losing 3 is going to be easier than gaining 5. If I lose 3, a +3 charge would be the result. All right, now let's flip this around. Let's look at our non-metallic groups. Group 5A, 6A, 7A. We're actually going to go backwards here. So going back to the periodic table here. Noble gases already have their octet. They are going to make no ions. They're going to make no covalent compounds for that matter, at least none that are going to be that stable. Now, do a little bit of reading, do a little bit of digging. You'll find that there are some compounds that exist between xenon and fluorine, but they're really unstable. Unstable enough that you put them in the presence of a drop of water, they instantaneously go back to what they were. Look at the halogens, starting with the fluorine group. Now we've got kind of the opposite scenario of the alkali metals. I've got 7 valence electrons there. I can either add 1 and get to 8, or lose all 7 and end up as a noble gas. It's the exact same logic as what we saw in group 1, but in the opposite direction. It's easier to add an electron than to lose 7. Well, if I add an electron, that's an extra negative charge. The ions that we would form are -1 charged. If I follow a similar kind of logic for group 6, 6 valence electrons, I can either add 2 more or lose all 6. It's going to be easier to add the 2 more. -2 is going to be the charge there. And in group 5, the nitrogen group, similar kinds of ideas. 5 valence electrons, I can either add 3 or lose the 5. It's gonna be a lot easier to add the 3. -3 is going to be the charge on most of these. Now we get to the middle. What do I do with the 4? And the answer there is actually really simple. They don't make ions all that often. And when they do, they don't tend to behave exactly the way that we would think of them behaving as well. So group 4 is very varied. You've got non-metal in carbon. You've got 2 metalloids in silicon germanium. You've got 2 transition metals in tin and lead. There's nothing very predictable about these. And so for the ones that do form ions, I'm looking particular at tin and lead. Problem with tin and lead is that they can form different ions. Transition metals, which we haven't talked about yet, have the ability, because of having not only the 2 valence electrons here, but also the electrons that are behind them. They have the ability to make different kinds of ions and still be safe and still be stable. So when it comes to transition metals, we usually use Roman numerals to help identify what ion they're forming. And that would give us the charge, obviously. So where we will be going on tomorrow is we've already kind of covered this spot here with the charges and the group relationship between them. What we're going to be starting to do is using this information to figure out the chemical formulas for compounds if we are given their names, and working backwards and determining names from formulas. It's a big part of this particular chapter. That's where a lot of the study is going to be focusing on, is on this idea of structure and naming. So I'm going to leave you with that. And so just as a reminder, nothing really due until Wednesday night. Again, once we kind of have a handle on where things are, I'll be able to start posting some of those assignments. For now, just start reading. You know, we've done section 1 in chapter 6. You know, look ahead to sections 2 and 3 if you want to kind of get ahead of a little bit of a jump on tomorrow. Have a good day.